Hi guys, you're welcome to this third series of reinforcement learning. So in this session, we are going to be looking at another very important concept in reinforcement learning, and that is policies. Okay, so we are going to look at the different approaches towards policies in reinforcement learning, and we are going to implement something around it. So policies. Okay, so what are policies in reinforcement learning? So a policy in reinforcement learning is a function whereby for a given state, we are determining what action should be taken. So in our last session, we talked about, the observable space. And in the observable space, we're able to look at different, observations, okay, or different, states that the agent can find itself. And depending on those states, we want to be able to decide what action should be taken, because at the end of the day, that is the goal of reinforcement learning. The goal of reinforcement learning is to have a good policy upon which, when the agent find itself in whichever state, it's being able to determine what action it should take in order to get a reward, or in order for it to be able to achieve its goal. Okay, so back to the example of the dog, that we had in our first session. So let's assume, the dog is running around within a compound, and then you come in, okay, you probably open the gate and come in, then the dog sights you. The dog must have been able to learn a policy whereby it's able to know what to do at that point. So maybe the dog has not seen you yet, and he knows the door is open. So maybe the dog is just going to run towards the gate to see who is the person that just entered. And if it is you, then it learns to sit so that you can reward it again. So basically, the goal of reinforcement learning is to have a good policy, okay, upon which it can act upon. It can be able to effectively determine the state, it should be when it's the next action to take when it is in a given state, or whichever state the agent finds itself, it knows the right action to take in order to be able to, get a reward, get a positive reward, and not to be penalized. So to define policy, so I'm going to say a policy is a given function. A given function, okay? A given function whereby given a state, okay, what action uh, should be taken. So given a state, it's able to determine what action should be taken. So that is the overview of what a policy is. So we are going to look at the core idea, what I'm going to call the core idea of a policy, right? Now, on this, sorry, before moving to core idea, we're going to look at the two types of policies. Okay, we are going to look at two types of policies. Let me see, policies. Okay. So I'm drawing two types of policy. The first one is what I refer to as the deterministic policy. While the other one is what I refer to as the stochastic policy. Stochastic policy. Now, for this deterministic policy, we are going to look at each of them in depth, but I want us to look at this. So for the deterministic policy, you are saying the policy of a given state, should determine its action. So in this case, you're able to have, a policy where for each state, for each given state that the agent encounters, we have a given action to it. That is a deterministic policy, where we have, okay, we find yourself in this position, this is what you should do. You find yourself in this position. So this is just like a an hard coded policy. This is not a length policy. And you know, the reality of agent, depending on the scenario it finds itself, is much more nuanced than just telling it, if you see it, go to the right, if you are this, do this. No. The reality of an agent is much more nuanced than just giving it hard-coded facts. Okay? And that will lead us to stochastic policy. So stochastic policy is going to determine the policy of a given of an action given states. Okay, so here we are going to determine the probability of the different probability of what action should be taken given a particular state. Does that make sense? So we are going to look at the probability of what action should be taken given a state. So in that case, we are not just giving a deterministic approach to it. We are giving a more nuanced approach. That's okay. If you find yourself in this state, the probability of going right is going to make sense. Maybe the probability of going right is maybe 60 better than going left. If you find yourself in this situation, the probability of going left is 70% better, or is much more 70%, good than going right. So, you find that much more, flexible pattern of being able to determine what approach you take it. And in this case, it is not hard-coded, it is learned over time. Okay, so that is basically that. So, so what does this pi mean? So this is pi. I believe we remember this Greek sign. So what this means, the standard policy of standard notation for policy. So this is the standard notation for policy. So we talk about the two types of policies. We talk about the deterministic policy, whereby we talk about for a given state, always do this particular action. So that is basically what we have there. So we have, the policy of a given state should be followed by this particular action. For every given state, do this, So that is basically that. But for the stochastic, approach, we are given a much more nuanced approach to it. For example, for a given state, the probability of this particular action is this. So let's say we find yourself in this particular state, 70% chance, to push right, or 30% chance to push left, and so on. So for the stochastic policy, you can have something like so let's say for the CartPole, for example, don't forget the CartPole example we gave in our last session. So this is the cart, this is the pole. We talk about the pole angle, the pole angular velocity. Talk about the cart position. Talk about the cart velocity. So for each of these parameters, now we are saying that let's take the pole angle, for example. So let's take the pole angle is, let's say, 30 degrees. Okay, the agent find its pole angle at 30 degrees. What action should be taken given this particular fact? Okay, we might decide to say, okay, pole angle is 30 degrees. Then we can say, okay, the action. So this is the state. Okay, this is the state, and this is the value gotten for this particular state. So don't forget we have two actions, left and right. Okay, so action for this particular agent in this particular observable space is left and right. So we have left, is left. No, let me clean this and draw it better. So you have something like this. Okay, this is left, this is right. These are the actions that can be taken. So we are saying to go left, let's say 30%. Go right. This is 70%, right? So you are saying this is 70%. This is 30%. So you are saying the probability of going right is going to lead to it's going to be better for the agent at that particular position than going left. So the agent decides, what to do in this particular case, and of course it goes right. So here we have. So what this happens? Why are we choosing a stochastic approach? Is because it helps the agent to be able to navigate the policy itself, to be able to navigate or explore the environment itself, and with that it's able to build its own policy. Okay. Okay, so here we oh, hi. Okay, here we're able to look at for the length policy, okay, of this agent. So because it is going to explore the environment, it is going to be able to determine what direction it should move given a particular state. So maybe during its exploration, when it is learning, when it is observing the environment, when it is exploring the environment, it has found itself in this particular situation, and it realized that for 100% of the time, when it found itself in this particular state, when it went right, 70% of the time, it's got its reward. Then maybe 30% of the time, when it's moved left, it got its reward, right? So for 70% of the time that it moved right, it got its reward, positive reward, and then maybe 30% when it's moved right, it did not. 30% when it moved left, it got its reward. 70% of the time when it moved left, it did not. So this is what is going to form the experience. So we as human being, that could be something like an experience, but to the agent, it is a policy that has been able. It's going to form a policy that it has been able to learn over time. In order for it to be able to navigate the environment when it finds itself in such state in the future. So that's basically what the stochastic approach looks like. So as a result, we are going to be looking at three policies, okay, three policy examples that we are going to be looking at, more especially for this CartPole example. Now, we're going to be observing three policy approaches. We're going to look at the random, approach. Random approach. Okay, so now for the random approach, here the policy is going to be looking like, let's say the policy of A, the policy of the action given the states is going to be 0.5. Okay, 0.5, right? Now, what does that mean? What that means is that the action to be taken, okay, the action to be taken given a state is 0.5 for all. Let me put for all here. For all action given state, right? For all action given state. So what that means is that when you find yourself, the policy of the action that should be taken for this random policy approach, okay, is that for the action should be taken, don't forget the action is left and right. So you have to take, 0.5%, right? So meaning for both left and right, it is what? It is 50%, 50%. 50%. So that is just pure luck. That is just pure luck. So meaning, if the agent is to go left, it can decide whether to go left or right. I don't know if that makes sense. So what that means is that if the agent finds itself in a particular state, it has a 50% chance. So the agent, the policy is telling it you have a 50% chance of getting it if you move left. You have a 50% chance of getting it if you move right. Okay, so that is, you can decide on which one to choose. If I have a 50% chance of going left or 50% chance of going right, then I just make a choice, because I cannot take both at the same time. I just make a choice. So, and in that choice is just pure luck. Okay, so this ignores So what happened with this is that this ignores all information. This ignores all information or length parameters. This is just pure log. Okay, it's just pure log. So it's log, right? It's just acting on log. So if you choose to move left, fine. If you choose to move right, fine. Just make a choice. So that is that, and that's problematic because it's not acting on intuition or knowledge or information. It's just acting on what it thinks, to do at that particular situation. So that is one. So we're going to look at the second example here. So the second example here is going to be the balance-aware approach, or the balance-aware policy. So the balance-aware policy. So what happens here is, and don't forget that in our last session we talked about the OBS index 2. So we said this is the pole angle, right? Now, this is the pole angle. So based on this particular observable information, based on this particular information, of the agent. So what action should be taken based on this information? Okay, so we can say something that, okay, if the angle is greater than 0, move right. If the angle is less than or equal to 0, move left. Okay, so that could also be another approach that is much more intuitive. Okay, we can decide to say, given this particular pole angle, OBS index 2, if OBS index 2, which is the pole angle, is greater than 0, okay, say push the cart towards right. Push cart, right. Right? Push cart towards right. Now, if OBS index 2 is less than or equal to 0, say push cart so you say push cart towards left. Okay, so this is also another policy that can be taken. But the problem with this is that this reacts to only where the pole is and does not reflect to how fast the pole is moving or how fast the cart is moving. So this reacts, let me say this reacts. The problem with this is that it is reactionary and it's reacts to only the pole angle and not how fast the pole is falling. So this could also be the same thing for every other factor as well in the between the cart and the pole. So another example that we could also look at could be the angle, the cart velocity, right? How fast, or maybe the pole angular velocity. We could decide to say, okay, if the pole angular velocity is greater than this particular value, then move right. If it is less than this particular value, move left. But that's also going to be reactionary to only the pole angular velocity and not the angle of that pole, or maybe the direction of the cart itself, or the direction of the cart itself, which is the position or the cart velocity. So all of these factors have to come up together for us to be able to make a holistic approach to be able to define what policy what policy will the agents be following to determine what direction it moves, when it finds itself in which state. So, for the balance aware approach, it's good. I mean, it's better than random approach, but also falls short on some criteria as well. So for the third one, which we are going to be looking at, which is the velocity aware. Velocity aware policy. Now, for this, don't forget that we mentioned that OBS index 2, which is the observable space, index 2 is the pole angle. And then we also mentioned that OBS index 3 is the pole angular velocity. Right? Now, very important. Now, so one thing we want to also, I want to also emphasize on is signal, right? So I'm going to want, I want to talk about signal here. Now, so what this signal does is, this signal helps us to define, the policy. Okay, this signal helps to define the policy, or it helps to tell us what actions to take given what. For the first one, for the first example that we have here, we can say the signal here is random. Signal here is random. Why? Because we have equal value or equal probability for the action that could be taken given a state. But for this, we are going to define a much more nuanced approach to this. So we can say the signal to this. You can say the signal to this is, let's say, the pole angle. That's the direction. We have a cut like this. Maybe the angle is like this. So you have something like this, so 0. Okay. So the angle, the pole angle plus 0.5 times 0.5 times angular velocity. Hmm. 0.5 times angular velocity. Now, so let's say this is a particular, this is the signal we want to use. Okay, we are choosing this. The angle times half of the angular velocity. That is the pole angle itself times half of how fast the angle is falling, or how fast the pole is falling. Because the angular velocity has to determine the velocity of the speed. How fast is it falling? Because we can only, the angle is not enough if we cannot track this the velocity of the pole itself. Because if it is falling so fast, we are going to be needing a much more different approach to be able to save it from falling, so that it can balance back. Or maybe if it is falling fast, it also affect the speed of the cart. If it is falling fast, we can say, okay, the cart should also fall fast, or maybe faster, such that it can counter effect the speed of the velocity of the pole angle. I don't know if you are getting what I'm saying. So let's say this is the cart now. So if this cart is falling fast, so we could want to say that the cart, if the pole angle, sorry, if the pole is falling fast, we want to say the cart should fall faster, such that it's able to balance it back by standing upright, because we definitely want it to stand upright. So at the end of the day, we're able to define, to be able to get this signal. So with that, we can say signal equals to BS index 2 plus 0.5 times OBX index 3. Okay, so if you're looking at this particular signal. Now, so we are saying if signal is greater than 0, to push right. How about if signal is less than 0, what do we do? Push left. So let's say this is the policy we are following, right? Now, what does this do? So we are saying the policy of a given state, the policy of a given state is equal to 1, right? If signal, that's pole angle plus 0 plus half of the angular velocity is greater than 0, else it is 0. So we are saying the policy of a given state is 1 if the signal is 0. Now, if the signal is 0, how do we get signal to be 0? If the pole angle is 0 and the angular velocity is 0. Okay, so because don't forget that we want the pole angle. Now, this is how the cat looks like. This is the pole. We are saying we want the pole angle to be 0, because in an ideal state, the pole angle is supposed to be 0. And if the pole angle is 0, the angular velocity will also be 0. Will also be 0. That is, the rate at which it is falling with time will be 0. The rate at which the pole is falling with time will be 0 as well. Because the pole, if this is standing like this, and it is not moving, and the angle of this thing is 0, it is upright, it is not moving, then the velocity is 0. If you park your car in front of your house, it is not moving, the speed is going to be 0. The velocity of the car will definitely be 0 because it is stationary, it is not moving. So that's basically what this is telling us. So the only way we can have this signal to be 0 is if the pole angle is 0 and the angular velocity is 0. So if the pole angle and the angular velocity is 0, then the signal is 0. So you are saying the policy of this state is that if the signal is 0, then the policy of the state is, if the signal is not 0, then the policy of the state is 0. So that is basically how that is okay. So what this helps us to do is that it helps us to also be able to factor in the velocity contribution, the angular velocity of the pole, because this is very important for us to be able to know how far, how fast, the pole is falling, and then also be able to counteract, so like I said, so we're able to counteract the angular velocity if it is falling too fast, by pushing the cart faster as well. So that is basically that. So we are going to go into some coding sessions now. Or before we go into coding sessions, so I'm going to write the policy as a function. The policy as a function, we have the inputs. So within the inputs, what do we have? We have the cart position. The cart position, the cart velocity. The pole angle. And then the pole angular angular velocity. Okay, so you have these four variables. So this is the input or the observable space of the CartPole that is being passed, that's being observed by the agent. Then this us to be able to, get a policy. We call this policy. Okay, so policy is some rules. Okay, rules for the agent to follow given a state. And then with this, we're able to have the output, which is the action. So for cat, we have left, right. I have 0 or 1, something like that. So this is what we are looking at when we are looking at policy as a function. We have the input, the policy, and action. The input is the observable space, the value we're able to get at each position within the state, and then that's based on the policy that the agent has learned. You're able to respond to, given this state, what action should be taken. So we're able to respond to what action should be taken, and that is the output, which is the action that should be taken. So that's basically that. A very interesting, thing to do. So we are going to be going into the coding session now. So here I'm going to create a new node here for this plus 3.py. So yeah, the first thing we are going to do, like we've always done, is to import necessary libraries. So we'll be using Gymnasium, NumPy, and Matplotlib library for visualization. So we are going to define some functions. So the first function I'm going to define is the random policy. Don't forget the random policy assign 50-50 percent probability to both actions, left or right. So in any state the agent finds itself, it tells it make a choice. You have 50% to go left, 50% to go right. So you just decide on what to do. So and that's like gambling, right? That's just like trying to uh, make a decision. I mean, just make a choice. Just lock. So np.random and then the choice, right? Yeah. So why? Because we have two. We have two options here: 0 or 1, left or right, right? So that's for the random policy. So for the second one, which is the balance aware policy, so you say balance aware policy. Yes, there you have the observable space. Here, don't forget the pole angle was OBS index 2, right? So we are returning here. Now, here we are returning 1 if pole angle is 0. Yes. Else 0. So what does that mean? Pole angle is greater than 0. Okay. So 1 is 0 for left, 1 for right. Now we are going to write if the pole angle is higher. If it is greater than 0, we are going right. If the pole angle is less than 0, it's falling left. So If the pole angle is greater than 0, that is, it's falling to the right, so we move right, right? 1, we move right. So, but if the pole angle is less than 0, that is falling left, is falling left, then we move left, right? So that's basically that. So that we can counteract the direction at which the pole is falling. Does it make sense? If you have a pole angle, if you have a pole, let's say this is a pole on the cart. My hand here is the cart. If the pole is falling towards the left like this, I mean, yeah, it's falling towards the right like this. You want your cart to move in that direction so that it can counteract the direction at which this pole is falling. And if the pole is falling towards left, you want to move towards left like this so that it can counteract the direction at which this is falling. If it's falling like this, you don't want to move this. If you move like this, then it falls. So you want to counteract. That's the balance away. So it can be balanced. That's why we call it the balance away policy. Now, the next one we have here is the velocity away. Velocity away policy. So here we have OBS. So we have important things that the pole angles. I'm going to copy this. Pole angle, pole angular velocity as well. Angular velocity, that's OBS index 3. Now we are going to define the signal for this. Don't forget that we said the signal equals to pole angle plus 0.5 times angular as the pole angular velocity. Now, what are we doing? So here we are returning 1 if the signal is 0. Else, we return 0. So what does that mean? If signal is greater than 0. Yeah, so what does that mean? We are moving right if the signal is greater than 0. What I mean, see, if signal is 0, signal can be only 0 if the pole angle is 0 and the angular velocity is 0. That is, if it is stationary. If the pole is stationary, then the signal is the angle is going to be 0, then the angular velocity is 0. If it is stationary, then we are only moving right. Okay? I mean, sorry, we are moving left. Sorry. If it's stationary, we are moving left. But if it is not stationary, we are moving right. So because we are keeping we are keeping aware also the angular velocity, that is the direction at which this is moving, not just the angle. So that's the velocity aware. I mean, sorry, the how fast this thing is moving, the pole is moving. We are keeping aware how fast the pole is moving and not just the angle it is. Because the angle is not enough to give us the information of how we can counteract it. Okay, how fast that pole is falling is also very important to us. So yes, you have this there. Then the next thing we want to do is we want to have a policy. So here we are going to define policy. Policy. So here we are going to have policy function. Number of episodes. You see number of episodes should be 30. So we have legal to do. There will be the policy rights. Now we are going to create the environment like we've always done. Change that to me. So here we have let's go. Here we have the words. to close this. So we have episode and episode and then episodes. So see OBS close. So you're going to reset EMV. So for each episode, you're going to reset. So you're not just that's it. So you have to tell. So you're going to create these variables, sensitive variables. Don't forget done will be false, so you can be able to track when it's done with each of these episodes. So say well, what's done? Why not done? So you have action equals to policy function. Now, so this is very much interesting because you can see that we're able to observe um, different policy function, not just random actions. You know, in the last two episodes, in the last two series, we've only been able to see random actions making decisions, you know, to be able to get reward. In this case, we're able to see much more intuitive approach towards making an action, towards determining an action. So that is that. Then here we have ABS word done and truncated. It was okay, truncated and info. Sorry. And info was so this is equal to EMV the step. Pass the action determined by the policy into it. To this, right? Now, so then the reward that is obtained are going to increase. So say total loss equals reward, right? Now, so if truncated, they will break out of the loop. That is, if we are done with this, we break out of the loop. Then for the function, what we return is no, within the loop, within the for loop, yeah, within the for loop, we return no, we append rewards. So we say rewards. Yeah, where do we have rewards? Okay, we have rewards within the function here, so we append the rewards. Rewards dot append total. And then once you are done with that, we close the environment. So see here let's close. All right. And also calculate the average. Calculate the average reward. Okay, that's me. Rewards. Right. So print some things as well. So you have this. So you print the average reward is this, the minimum reward is this, the maximum reward is this. So you're able to keep track of the average, minimum, and maximum reward. Okay. Then also you're going to define a function to show policy decisions. So here you have a function that shows policy decisions, how it makes its decision. And then you're going to have a function that also visualizes the graphs. Then they can probably run this. Okay, so what we want to do here is we want to print important things. Okay, here we have random reward. Yeah, random policy. Okay. Then also we have balance aware policy, rest aware policy. So we have those three, each of them running on 30 episodes, and then it plots the graphs, plots the policy decision. We visualize the policy decision, and then plot the graphs. So let's take a look at that. Okay, so let's run this. Let's see. Okay, so you can see. Okay, before we go into this, okay, now you can see this. Okay, yeah, you can see. So for the random policy, you can see the average reward here is 21. The minimum is 9. The maximum is 61. For balance aware policy, you can see the average is 43. The minimum is 25. The maximum is 65. So for velocity aware, you can see everything is just 500 across the 30 episodes, which is very impressive because you can see that the more nuanced the policy is, the more comprehensive the policy is, the better the reward. The better the reward, because in this case, the agent is able to make better decisions on what action to take given a particular state. So you can see, based for the policy sample decision, okay, so you can see slight tilt right. So when it slightly tilts right, for random policy, it tells it right. Balance policy tells it right. Velocity aware also mentions right, right? So you can see random is just telling it right, 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 right. For whatever situation, it's just right. For balance aware, it's still more nuanced, but mostly right. But for velocity aware, it's much more intuitive because it's considering many factors. Okay, for it to be able to determine what position or what it should, what action should take given a particular state. So that's very interesting. And then for the graph, I'm going to be showing the graph now. So here is a visualization of the graph. So you can see what we have here, random aware, is this one down here. You can see it. Balance aware is this one up here. You can see it's just slightly above balance aware. But for velocity aware, it's up here. That's maximum reward obtainable, right? And then, that's maximum reward. Okay, so which is very impressive and very interesting. So what this has been able to teach us is, rather than just making random decisions, you make stochastic decisions that are more nuanced in their approach, considering the different, observable states that the agent experiences. In this case, we're only able to act, based on the pole angle, the full angular velocity, and then with that, we're able to make a decision on what direction we should push the cart. So that's just it. I think it's very interesting. So this is where we are going to be stopping today, and we meet again in our next session. So if you enjoyed this video, kindly like, subscribe, and share this video to your loved ones. Thank you.